Let's imagine that I have a section of pipe that starts at one thickness and then travels to another. I'll pick a particle and give it a velocity v1, and it is traveling in the vicinity of an area called a1. Then the pipe narrows, and our particle now has a velocity v2 and is traveling in a new area a2. Since a liquid is incompressible, I have to have the same amount flowing in as I do flowing out. This leads us to V1A1 equals V2A2. Let's imagine now that I have a pipe that goes from one height to another. We know from kinematics that if I take an object and move it from one height to another, then work is done. So if I start at a height y1 and end at a height y2, fluids are so massive that it must have taken a force to do this, and that force comes from pressure. There is also a change in kinetic and potential energy. The scientist Bernoulli took our conservation of energy equation and applied it to fluid dynamics. Now, this equation looks confusing because of all the p's and rho's and y's and g's, but the p's are pressure, the rho's are density, and the v is velocity. Let's take a look at this sample problem. Let's say that I've got a large silo of, let's just say it's water, and it's at a certain height. Now, this pipe leads to another section of pipe where I have a really pretty fountain. Yay, pretty. Anyway, now, I have a large area here, and this area can be considered so large that the height isn't really going to change a whole lot. So I start at a height y1, and then I end at a height y2. So I have an overall change in height delta y. Now, that initial velocity can be considered 0 because that height doesn't change. Now, what's the pressure? The pressure exposed on my water in the silo is the pressure due to the atmosphere, as is the pressure from the water spewing out, because both are open to the air around them. Let's try this example problem. Let's say I've got a two-story house and I've got a pipe coming in, and let's say that this pipe has a diameter of 2 centimeters. Now, this pipe flows in and then it goes up to the second floor. Now, the initial pipe has a pressure of 4 times 10 to the 5th pascals. The second floor is 5 meters high, and the new diameter of my pipe at the second floor is 1 centimeter. My initial velocity intake is 1.5 meters per second, and I need to know what is the velocity at the second floor, what is the pressure at the second floor, and what is the volume flow rate. Volume flow rate is given to us as the change in volume over the change in time. To solve, you need to start with our first equation, V1A1 equals V2A2, and the area is pi r squared. Now you can solve for V2 and use Bernoulli to solve for the rest of the problem. I would take a moment and pause this video to solve the rest of the problem. The answers you should have gotten are 6 meters per second, the pressure in the top pipe as 3.3 times 10 to the 5th pascals, and the volume flow rate as 0.47 liters per second. One of the most crucial things you can take from this section is that faster moving liquids have a lower pressure, and this is what allows fluids to flow. I don't think I need a drawing to illustrate to you what a problem it would be if fluids didn't flow right.